All right. I'm going to try and be quick this afternoon. I know I'm the last presentation slot. Thank you all for sticking around for this. I know it's late in the day. We're all tired, but I'll try and make this as painless as possible, I swear. So the robotic installation of the fastener film material. So on the F-35, there are 25,000 fasteners on the OML surfaces. And Lockheed has developed, in partnership with an outside vendor, a proprietary material it's a thermoplastic that we can install and smooth out the entire OML surface by installing this plastic over the fastener heads. And that increases the aerodynamics of the aircraft, as well as, apply some stealth technology to mask the fastener heads. The general process, it's fairly involved. It starts with an IPA wipe to basically activate the titanium fastener head, followed by a promoting step in which, we go out and we apply promoting material to help all the additional layers adhere. Then we'll go out with our normal non-chromated primer, prime the fastener head. Then we'll actually go out and install what we call hot dots, which is the thermoplastic proprietary material to the promoted fastener head. After an appropriate amount of time, we have to come back and then skive it. We have to perform what we call a cold skive as opposed to a hot skive, which requires the material to cool down back to room temperature. And we've done a lot of testing on that, and we've determined that the reason we have to do a cold skive is because once the material cools, the reheating from the skiving process allows for the material to flow better, and we get a lot less defects from it. After it's been skived, we'll go back with what I call a scorecard. We literally have a 3x5 index card of a grading scale and a flashlight. And the flashlight followed with the index card helps you to figure out, here's on a scale of, X to Y, how good of a job did I do? If you did a good job, good for you. It's difficult to do. I know I don't do perfect fills, and I've been doing them for 2 years. So a lot of times you'll have to go back and do repairs to fill in a lot of those defects that you'll see from the skives. And I have some images of that on the next slide. Once you're all set to go and you're good, what you'll do is you'll take one final sanding operation using a jitterbug. That's just a quick brush over each of the fastener heads to maintain, like I said, the flushness of the material to the OML surface there. So we get a nice, smooth, continuous, uniform surface to the entire aircraft. And so you can see some of the images here. We have a sponge roller. That's what we use for the priming and promoting processes. The process there is really super duper low tech. The painter will go in with these sponge rollers, dip one of the ends in the material, and actually go out and dab it and physically touch each fastener location, followed by the cure time for each the primer and the promoter. And that's how we'll prep all the fastener heads. Then a little orange box there, that's what we call our hot iron. That's what the operators will use to actually apply the hot dot material. And that basically functions as because the material will locally melt when touched with high enough heat. So we'll use the hot iron set to a defined temperature, go over to what we call the hot dots, literally touch the hot iron to a hot dot to pick it up, because it'll locally melt and then stick to that brass tip. Then we go out and we just smear it in there. Then you see the flashlight for the inspection and the post-process sanding. So the big issues with the process is it's manual. So like I said, I've been doing the hot dots for 2 years, still nowhere near perfect. It's a very labor-intensive process. It's a lot of guys up here doing this all day in a non-ergonomic stance. Sometimes they're bent over doing like that or coming down. Really, you can be in almost any orientation to do this hot dot application, because the aircraft, as it moves through our production line, changes orientation. So the fasteners may not always be in the most accessible locations. It requires skilled labor, very, very much so. We only have, I think, we have about 40 guys on site, roughly, who can do the hot dot process total. Of those 40, I'd say only about a dozen can do it consistently well. So the defects that you'll see, and so you can see in those two pictures here, there's some defects going on. This material is quite grainy. I said it's a plastic matrix with some alloy materials in it. So a lot of times what you'll find is if you skive too quickly or too slowly or it's too hot or too cold, you end up with these big recesses of material that are missing. And the last thing that, a big issue that we found out recently from our department is that apparently melted plastic is bad for you. You shouldn't breathe it in. I know that comes as a big surprise to everybody in this room, but that's the case. The repeated process of picking the hot dots up with the hot iron creates literally whiffs of smoke that our department has recently deemed to be non-hazardous, thank goodness, but breathing in plastic is still something we would try to alleviate, and that's where I think the automation really comes into play. Let's see if some of these videos work. If I click, maybe. Maybe click again. Is that playing? Okay, there it goes. So I can't see it on this screen. So what you're seeing here is our dot dispense system. This basically is a tower of hot dots stacked up with a weight pushing down. Then almost like you're playing shuffleboard, you have a little hook that pushes a dot out to a specified location for the robot to drive to. Then what we'll do is we'll take that hot iron, like I said before, the manual process, it'll come and touch down and pick up that dot and then drive back to the part to do the installation. Here what you're seeing, the robot, after it's picked up the dot, is going to come to the part and actually come out and smear that material in, smear it into the fastener recess area there, followed by a second smearing operation to further, really mash the material into the fastener recess. And that's just in an effort to really make sure that the whole fastener head is covered uniformly, and that we'll have some excess over the top of it to skive off. One thing you'll notice in here that I haven't really touched on is the scanner that's kind of hanging out behind the hot iron there. That's a micro epsilon scanner. It's a single laser line scanner on a slide. That scanner actually serves multiple purposes for the fastener fill process. First and foremost, we're using that scanner to locate the part within 3D space. After the part is backed into our tooling and mounted up, we're actually using that to go to drive to known fastener locations and scan them to find the center point of the fastener head in 3D space. And once we have 3 fasteners lined up, we can do our 3-phase transformation to align the part to the robot. Secondly, the scanner is capable of doing all the what we call pre-fill inspections. So that's going from fastener to fastener and scanning to get the accurate fastener depth, as well as any positional variation that's going on there. So that way we can know if we need to put in one hot dot, 2 hot dots, 3 hot dots. All this stuff varies by diameter anyway, but the depth there also plays an important factor because we have to have enough material to skive off at the end. And finally, that scanner is utilized for the post-fill inspection, where after we've skived off all the excess, we go back and check for all those missing material areas like we saw in the previous images. So what you're seeing here is the robot doing its skiving operation. It's pretty self-explanatory. It drives up to a known location below the fastener depth, touches off on the part with a defined amount of force, and then skives up through the material to a point after the fastener head is after the center point of the fastener, before pulling back with the excess skived material. All this is currently being done on a KUKA Evo robot. The collaborative factor there helps us to delineate the force requirements needed for each of the tasks. However, this year we're also investigating changing that end effector a little bit to use an industrial application, industrial robot with a load cell in the tool changer. Like I said, the micro epsilon scanner does all of our metrology work. So what you can see here in the image on the far left is the scanner itself set up on the slide that will, like I call it rastering, raster through. It produces a very, very dense point cloud. The spacing there between points on the laser line is quite dense, and the slide, as it pushes the scanner through, creates a very tightly knit point cloud of data to collect there. So what you can see here is moving to the middle image, and then the far right image is just a representative scan. This wasn't done by the robots, but this is just a representative scan of a fastener fill that has some defects in it. And as you can see, it translates quite well to the scanner output there, where you can see defect 1 and defect 2 and how they relate. And you can see that the red circles are highlighting where those defects are and how much deeper they are than the nominal OML surface. Moving into the 2017 development. Okay, just wondering. Moving to the 2017 development that we're doing this year, we've actually generated a representative coupon based on our first implementation area, which is the F-35's forward fuselage. This coupon, not only has contours in one direction, but also some complex contours and some flat surfaces to work around. So what we're seeing in this image is our representative coupon that we've designed and made up, as well as what we're calling the fill and skive lines. Part of the skiving process per our manual spec is to follow the major contour, no matter what it is, with the iron oriented so that it's always flush to the surface. That's in order to ensure that the fill and the fill material follows the flushness of the OML across the aircraft there. Because if you can imagine, if the fill is this way and you skive in this direction, you're going to cap it off, and then you're going to have a low fill there. Moving into some of the simulation work we've done so far this year. I said this is still looking at our EVA robot, but this is a simple locating it to the aircraft and going and touching off several points and doing some preliminary reach analysis to see how many points we could hit with the EVA in this orientation here. Since this design has come out, we've already made some significant modifications to it to help it reach more fasteners, and I'll have to translate along the forward fuselage there as needed to really hit the entire work area. So to follow in the simulation, these are also some of the images that we get from the micro epsilon scanner. They are basically the brown areas there represent and the green areas represent intolerance bits, whereas the blue, and you can see the scaling on the bottom, without getting into the details of what the actual dimensions are, where you can see on the left-hand side is a fastener that's been adequately smooth to generate a flush surface, whereas on the right-hand side is some kind of a smoothing algorithm with parameters outside what we'd call nominal, and those produce failing results there. So this is all still development. It's a lot different than a lot of the other presentations today. It's not related to drilling. It's not related to milling. This is a whole new kind of a foray for Lockheed Martin, I think in general for robotics, doing this kind of an application where you're touching the part in a non-normal kind of sense. And so we made significant strides so far with this development, which will wrap up at the end of this year. And the nominal plan for implementation is we'll have some kind of capital funding available next year to start writing an actual spec and go out to AIT, who is our robot integrator there, to actually start making this work cell a reality. So we're anticipating right now having an installation in Fort Worth, Texas, and somewhere in the middle of 2019 range, with our first article coming in Q3. And then follow on from that is an expansion into our wing line, so doing our lower wings, our upper wings, our mate platforms, trying to automate as many of these fastener fills as possible to bring up the quality of the aircraft. Any questions? All right, thank you. Oh, hang on. So that's actually kind of a tricky question because, like I said, it's very operator dependent. So the primer and the promoter each have cure times attached to them. So after you promote, basically the part has to sit for X amount of time before you can go back and start applying the primer. Same thing with the primer. After it's applied, you have to sit and wait for Y amount of time for the primer to cure before you can go back and start doing your hot dot process. To answer your question, to go through and do one dot really varies from person to person. The fastest guy does a dot in about 40 seconds. The slowest guy takes about 2 minutes. So some of that's dependent on the guy. It's also dependent on the build area, how complex the contours are there. It's a lot easier to do a fill on a flat surface as opposed to a contour, let alone a complex contour. And so I'm not trying to make a pun here, but it is a learning curve. Yeah. Mm-hmm. Honestly, there's not really that many areas on the aircraft that have contours that complex, because the fastener head themselves are only, a half inch wide. Everything locally follows one major direction. Well, thank you.